Okay, let's unpack this. You've got a critical application, right? Maybe handling millions of users. And it's time for an update.
Yeah, new feature, maybe a security patch, performance tweak.
Hmm.
Something needs to change.
Exactly. So how do you push that change without, causing a service interruption, or worse, bringing the whole thing crashing down? This is where Kubernetes deployments really shine. They're an incredibly powerful resource, especially for managing those stateless applications.
Right. They do more than just keep a certain number of your app instances running.
They absolutely do. They orchestrate that whole complex dance of updating them. Today on the Deep Dive, our mission is really to peel back the layers on two fundamental but maybe often underestimated features within Kubernetes deployments. The things that make seamless updates and crucially rapid recoveries possible: rollouts and rollbacks. We've distilled the essential knowledge from a detailed exploration called Kubernetes Deployments, Rollouts and Rollbacks Explained.
And I think for anyone building or managing applications in Kubernetes, really getting rollouts and rollbacks isn't just like a technical detail. It's foundational.
Foundational, yeah.
It's key to operating resilient systems. It sort of moves you from hoping updates go well to basically ensuring they do, or that you can recover quickly.
Okay, so let's start right at the heart of it. Kubernetes deployments. What are they fundamentally?
Well, at their core, they abstract away the complexity of managing groups of identical application instances. Pods, usually.
Right. They make sure your desired number of pods are always running, and they're the main way you evolve those applications over time. So within that framework, we first have the rollout. This is the, let's say, deliberate process of updating your deployment to a new version. Kubernetes does it meticulously, replacing old application pods with new ones.
Gradually.
Gradually, yes.
Right.
Ensuring continuous availability. It's the reason your users probably rarely, if ever, notice an update is even happening.
And then the flip side is the rollback.
The safety net.
Exactly. If that shiny new version introduces unforeseen issues, a critical bug, maybe eats memory, or just crashes outright.
Yeah, it happens.
A rollback is your strategic retreat. It lets you quickly revert your application back to a previously stable, known good state. It's like your ultimate safety net in this fast-paced world of continuous deployment.
So why are these built in? What's the real advantage over just, say, stopping everything and starting the new version?
Well, the benefits are huge.
First up, seamless updates. Your application stays available throughout the change. That's like non-negotiable for production.
Absolutely. Then there's reliability. Rollbacks give you that immediate recovery mechanism if an update fails.
And automation, this is big. Kubernetes handles the tricky orchestration of swapping pods or reverting them. Cuts down massively on manual effort.
And potential errors that come with that.
Right. And finally, scalability stays intact. You keep the desired number of application instances running throughout the whole update process. Performance doesn't just tank.
And when you interact with deployments, you're actually tapping into this whole coordinated system. Your declarative YAML config. That gets processed by the API server. It stores your desired state in, etc. Kubernetes distributed database, basically.
That persistence is key for the history, right?
Exactly. Makes the revision history durable. Then the deployment controller orchestrates the changes, usually managing replica sets.
Which manage the pods.
Right. Replica sets ensure the correct number of pods are running on the nodes in your cluster. And you manage and watch all this using kubectl, your command line tool.
Okay, let's dive into how rollouts actually work then. It really is the art of the seamless update.
Yeah.
Kubernetes deployments, they operate on this declarative model. You, the user, define the desired state, usually in a YAML file.
What you want it to look like.
Exactly. And Kubernetes works constantly to make sure the cluster matches that state. Rollouts are a core part of this, letting you update container images, configs, resource limits, all without downtime. Now, the default strategy, the one you get out of the box, is the rolling update strategy.
The most common one.
Yeah. This is where Kubernetes intelligently, gradually replaces old pods with new ones. Think of it less like replacing a whole bridge while traffic flows. Maybe more like swapping out individual bricks in a wall carefully so the structure never fails.
That's a good analogy. And crucially, you, the operator, get granular control over how this gradual process happens.
Do those parameters.
Yes, the key ones are max surge and max unavailable. Max surge dictates the maximum number of extra pods Kubernetes can create above your desired replica count during the update.
So how fast it can scale up the new version?
Sort of, yeah. It controls how aggressively new pods are spun up. Conversely, max unavailable sets the maximum number of pods that can be offline unavailable at any single moment during the update.
Ensuring a minimum level of service.
Precisely. And what's often overlooked is that tuning max surge isn't just about speed. It's a strategic choice.
How so?
Well, it impacts resource consumption, right?
Yeah.
If you surge too high, you might need more node resources temporarily. It also affects the blast radius if the new image is bad.
Ah, right. More new pods failing at once.
Exactly. It can even trigger cluster auto-scaling you didn't expect.
Yeah.
So finding the right balance there, that's key, and it's something many people don't fully consider.
That's a really critical point. So while it gives us control, there's also this subtle art to balancing that control against efficiency and risk. Okay, let's walk through the actual flow.
Sure.
You start by updating your deployments YAML. Maybe you change the container image tag from v1.0 to v2.0. You apply that.
kubectl apply dask in deployment.yaml.
Right. Kubernetes sees this change. Behind the scenes, it creates a brand new replica set just for those v2.0 pods. Then the gradual replacement begins. New v2.0 pods are created. Old v1.0 pods are terminated, all while trying to maintain your desired overall replica count, respecting max surge and max unavailable.
It's a controlled handoff.
Exactly. This stance continues until all the pods are running the new v2.0 version. And Kubernetes is constantly monitoring their health, their readiness throughout the process. So ultimately, the power of rollouts really boils down to a few core things. Zero downtime, because some pods are always serving traffic. You get controlled pace through max surge and max unavailable. You decide how fast or slow, how risky or safe the update is.
Right, you tune it to your needs.
The automation is huge. Kubernetes handles the orchestration, freeing up your team.
Less manual toil, fewer mistakes.
And inherent flexibility. You can update images, environment variables, resource limits, labels, pretty much anything in the pod template.
Okay, so that's the happy path. The rollout goes smoothly.
Right.
Now, connecting this to the bigger picture, rollbacks are for that critical what if it goes wrong scenario.
Yeah, the inevitable oops moment.
Exactly. They're designed to rescue you when an update introduces issues. Could be a subtle memory leak, could be a critical bug that only shows up under production load, or, just outright crashes.
So how does Kubernetes know what to revert to? It can't just guess the last good version.
Ah, good question. It knows, thanks to its revision history, every time you successfully update a deployment, Kubernetes records that change as a distinct revision, numbered usually.
Okay.
This history, because it's stored durably in Alice, etc., essentially gives you a timeline of your deployment's changes. Each revision points to a specific replica set managing a particular version of your pods.
So it's like version control for your deployed application state.
That's a great way to put it. It's like having, well, maybe not infinite, but a configurable number of undo buttons for your infrastructure state.
And describe the rollback process itself. Let's say that v2.0 update starts failing, pods are crash looping. What do I do?
So if that v2.0 update is causing problems, you can simply tell Kubernetes, usually via kubectl, to revert to a previous stable revision. Let's say revision 1, which was our v1.0.
Okay.
What happens then is Kubernetes acts immediately. It scales up the old replica set, the one managing v1.0 pods, and at the same time, it scales down the faulty v2.0 replica set.
Ah, so it reverses the rollout process, essentially.
Pretty much, yeah. The result is your application instantly reverts to its last known stable configuration. Functionality is restored, hopefully with minimal user impact. You initiate this yourself, specifying which revision to go back to.
Kubectl rollout, undo deployment, my app to revision 1, something like that.
Exactly like that.
Okay, let's pull back the curtain a bit further. How does Kubernetes actually orchestrate all this, both the rollouts and the rollbacks? It involves coordination, right, between the control plane and the nodes.
Absolutely. It's a continuous, intricate coordination. It starts when you modify that deployment YAML, like updating the container image, and you apply it using kubectl. The API server gets it first. It validates the YAML checks if it's structured correctly, and then stores your updated desired state, etc. Makes it persistent.
Got it. Then for a rollout.
During a rollout, the deployment controller, which is constantly watching for changes, notices the update. It's the main conductor here.
Okay.
It creates the new replica set for your updated pods. Then the scheduler steps in. It finds suitable nodes for these new pods based on resources, constraints, etc.
And assigns them. Yeah.
Then the kubelet, which runs on each worker node, gets the instruction and is responsible for actually starting the new containers defined in the pod spec.
And while that's happening, the deployment controller is also telling kubelets to terminate old pods.
Correct. Gracefully terminating the old ones, always keeping an eye on maintaining availability based on those max surge and max unavailable settings we talked about.
Okay, and the rollback flow, how does that reverse?
So if a rollback is triggered, you run that kubectl rollout, undo command the flow reverses, orchestrated again by the deployment controller.
It looks at the revision history.
Exactly.
Yeah.
It identifies the replica set associated with the previous stable version you want to revert to. It then scales that replica set up.
And scales the problematic one down.
And scales the current problematic replica set down to 0. The kubelet on the nodes then gets the updated instructions. Terminate the faulty containers and start the containers for that previous stable version.
And what's really empowering, I think, is that you maintain visibility throughout all this.
Totally.
You can constantly monitor the status of your rollout or your rollback, check the health of individual pods, all using familiar kubectl commands like rollout status or get pods.
Yeah, it gives you immediate feedback and pretty robust control over the whole life cycle. You're not just firing and forgetting.
So when we put it all together, the combined power of rollouts and rollbacks, their effectiveness is pretty remarkable, wouldn't you say?
Oh, absolutely. You get vastly improved reliability.
Yeah.
Rollouts aim for smooth updates. Rollbacks provide that rapid recovery from failure.
Huge automation. Kubernetes handles the complex pod juggling during both processes.
Yeah. Creation, deletion, scaling. It's all managed. The history tracking through revisions is invaluable. Makes reverting to a stable state straightforward.
You don't have to remember what the last good config was manually.
Exactly.
Yeah.
And finally, scalability is inherently maintained. The desired replica count stays consistent, ensuring performance doesn't dip unexpectedly during an update.
Okay, so we've really peeled back the layers on how these mechanisms operate, the controllers involved, of the parameters. Now, the crucial question for anyone listening is, how do we translate this understanding into, actual practices? How do we make our applications more robust and maybe our lives a bit easier?
Right, the practical side.
Yeah, here are some best practices we've kind of distilled. First, and this sounds obvious, but test your updates rigorously.
Always, please.
Validate new versions in a staging or non-production environment before you even think about touching production.
Absolutely critical. Second, strategically set your update parameters. Don't just accept the defaults necessarily.
Sure.
Think about max surge and max unavailable. Configure them carefully to find that right balance for your application between update speed and availability. It's not one size fits all.
Good point. Third, monitor your rollouts relentlessly. Use kubectl rollout status or other monitoring tools. Watch the health of your new pods as they come online.
Catching issues early is key. It can prevent a small glitch from becoming a full-blown outage.
Definitely. Fourth, preserve your revision history. Don't set that revision history limit in your deployment spec too low.
Yeah, you might think you're saving space, and etc., but
you lose rollback options. You want those older, stable revisions available, maybe even from weeks ago, just in case.
good insurance policy.
Finally.
Use version control. Store your deployment YAML files in Git or something similar.
Oh, yes. Infrastructure as code.
Exactly. It gives you an audit trail, makes collaboration easier, and ensures you can always recreate any desired state from a trusted source. So ultimately, rollouts and rollbacks in Kubernetes deployments, they're more than just features, aren't they? They feel like foundational pillars. They really are.
Pillars for achieving genuinely seamless application updates and ensuring that rapid, reliable recovery if things go sideways. They're managed through that elegant declarative YAML model, leveraging Kubernetes' powerful control plane and nodes for incredible automation. It just makes deployments an absolute cornerstone for building scalable, resilient systems in this whole cloud-native world.
It really does. And maybe, thinking a bit broader, a final thought for you listening. Consider this principle of controlled, gradual change with the ability to quickly revert. How does that apply to other complex systems you deal with, maybe even outside of technology entirely? What new possibilities does thinking in terms of rollouts and rollbacks open up for you, beyond just deploying code? Something to ponder.
That's a fascinating question, a great place to leave it. Thank you for joining us on this deep dive into Kubernetes deployments. Keep exploring, keep learning, and we'll see you next time.